Okay, so very good evening and welcome to Physics for Students, lecture number 5 on classical physics. And today I would be basically taking you through the past lectures which we have done. So anybody who have missed those earlier lectures 1, 2, and 3, you don't have to worry because 1, 2, 3, and 4. So I would be taking you through the entire understanding of those 4 lectures so that the basic understanding of those foundations of classical physics will be done. And once we are done with the understanding of the classical physics, then what happens is that we are ready and good enough to start with the basic mathematics and other further areas of classical physics. So first of all, I would like to give you a quick understanding what we are covered. So in case you're unable to understand, please do let me know. This is basically what I have talked about the first 4 very important lectures, which brings out the idea of classical physics, the foundation. So what we have seen is that classical physics basically refers anything which is before the advent of quantum mechanics. That means after quantum mechanics, it becomes quantum physics. Again, as I told you earlier, that it is nothing which is related to modern physics. Modern physics is something which starts of a new era or something. So classical physics will basically include Newton's equations, Faraday's law, electromagnetic, and Einstein's general theory of relativity, which in numerous occasions I have described that it is also a classical theory. Okay, so we learned something of this, which is called a Laplace demon. And what this demon tells is that if human beings or any superhuman being, say for example, is able to know the precise location, for example, momentum of every atom in the universe, their past and future for any given time, then we can calculate the future from the laws of classical mechanics. This was actually, yeah, Rudra, namaskar. This was actually formulated by the famous physicist Pierre Simon Laplace in 1814, and it was called the area of causal determinism. Causal determinism means which is actually there is a cause, there is a reason why this is there. So, some people were telling me that, theory of everything, etc., was started with string theory or even Einstein's theory. No, it has started much earlier. Even 1814, Laplace, imagined to have a theory of everything. So we also saw that classical physics is basically consists of a set of rules, set of principles, and what is the underlying logic behind it. So basically, if I know everything about a system, then we can say that if I know everything about a system at some instant of time, say right now, say for example 9:18 p.m. today here in India where I'm sitting, if I know certain things, then I can predict, and there are a set of rules which will govern what will happen in the future. Now, I also posed an idea when I talked about what if it is not an instant of time, but when it is spread over a long time. That means classical physics is given one position of time. I'm saying no, it is not one position, but rather if it happens that we spread out through a long range of ideas or time. So we get something which is called non-locality in physics and quantum entanglement. That means certain physical phenomena can be correlated or even entangled in ways. That means this part and this part are not independent, but something which is entangled with each other. That actually gave rise to violation of locality. Locality means something which is traveling either at the speed or lower than the speed of light. But when we talk of quantum entanglement, that means something which violates the locality, and knowing the state of one particle instantly affect, or we can know that what is happening on other. And this violation of locality is something which is not in the framework of classical physics. So this kind of non-local behavior is not possible in the framework of classical physics, which assumes that things propagate always at a finite speed. At any instant of time, we can determine only by its local history. So that means what I told you over here, that if it is not an instant of time, then we are moving out of the arena of classical physics. So from here we come to know that that is what we mean, that when we saw the laws of classical physics are deterministic, we can say that the same thing but with the past and future reversed. Such a system is called a reversible system. We also talked about what is a reversible system. For example, a system that can be returned to its exact initial state. For example, a pendulum which is going to and fro, to and fro. So if I know the initial conditions of the pendulum over here, I can know what is the final condition. That is what is called a reversible system. There are many examples which we have seen: a ball bouncing, isothermal expansion or isothermal compression, all those things. Here I would also like to tell you, which I have skipped here, is that one particular subscriber asked a very good question. I did a detailed research. Is Heisenberg's uncertainty principle local in nature? So I explained in the earlier lectures that it might be local and might not be non-local. And we also found out the two researchers who showed that non-locality and Heisenberg's uncertainty principle, how they are related to each other. So these are few of the key characteristics of a classical physics. That means it has to be deterministic. That means the system evolution is governed by deterministic laws. That means the future state is uniquely determined. Microscopic reversibility. That means if a pendulum is swinging to and fro and to and fro, each and every electron, proton, neutron, all those at the microscopic levels would be giving back when it comes back. That means the future and the past, all the microscopic things are also will be the same. Will pendulum work in space or zero gravity? I don't think so it is going to work. Because pendulum working in zero gravity, will pendulum work in zero gravity? I think that we can do this kind of an experiment in zero gravity, and then we can find it out. But as far as my thing goes, the pendulum will not move in zero gravity. It will stay as it is. Because the gravity, because gravity is one of the two main forces, Rudra, which affects the pendulum at a given time. And it helps to move back and forth and back and forth. So gravity, I would say, is very consistent force that always pulls the pendulum. So in case of a zero gravity, I think the pendulum won't be moving. Richard Nolling is saying agreed. Okay. And there is no dissipation of energy also. That means no energy is lost or gained during the process. That means if I'm moving from here to here, and when coming back, there is no loss of energy. And very importantly, we talked about the isolated system, meaning there is no exchange of matter or energy. From here, if you all remember that we talked about what are called exact solutions of Einstein's field equations. That means what is that we are taking a kind of a very isolated system, symmetrically spherical, symmetric, no charges, etc. And that makes the equations of Einstein's field equation much more easier. So we always in classical physics try to take a kind of an isolated system so that the external interventions might complicate the system too much. We also learned what is a system. When we talk about the system, so it is basically a collection of objects that are interacting with each other. And also we learned, most importantly, what cannot be considered as a system, because individual elements, isolated systems, abstract concept without any real world counterparts, randomness, all those things. So isolated system, random occurrence, open-ended collections, abstract without any real world applications, a lack of coherence or organizations. We also saw what is called the space of states, and I told you this is extremely important because you will see this space of states will slowly and slowly get accumulated in your brain when we move into quantum state and quantum computation. So what we saw, that basically it is very simple. It is a collection of all states in a particular system, and it is not an ordinary space, it's a mathematical space. So in classical physics, the state of a system refers to complete description. So if you've got a cup or a ball, etc., so a complete description which will actually describe everything. So if I get a kind of a coin which has only a head, then the future is very simple, it will only show a head. So the system has only one state, and predicting is very simple, it will only have h. If you get a kind of a H to T, but here we need to move from head to tails. And remember that in a kind of a classical system, we get something which is called a continuous system. That means there are no discrete jumps. But in case there is a jump, we call it a stroboscopic effect, which is a kind of a phenomena caused by aliasing that occurs in continuous rotation and shift. So in classical mechanics, because we assume that systems evolve smoothly, so we call it continuous, and if it is not, we call it stroboscopic. So given a head and a tail, the system will evolve with head as head, 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 and with tail it will evolve as tail, tail, and tail. I'm not taking from head to head, head to tail. I'm just taking head as one state, tail as one state. Now you see, if I take a two-state system, that means from H to T and T to H, the system will evolve as HT, HT, and if I start with T, it will be TH, TH, and so on. So degrees of freedom, say for example, for H would be sigma equals to 1, and for tail it would be sigma equals to -1. So first equation, sigma n plus 1 equals to sigma n, tells that there is no change, and if there is a minus n, that means there is a state flips, it actually changes. Here you see it is a 6-state system. So from 1 to 2 to 3, 4, 5, 6, and again, so it is an endless cycle, right? So it is called a 6-state system. And it is typically, if we want to quantitatively denote the number n, which is moving and incremental, then we call it as n plus 1. We also get this kind of a state which is called a 2 cycle. Now you see, if I start with 2, I will go to 6, 1, 2, 6, 1, 2, 6, 1. That means I'm never going to go to 5 or 3 or 4. Similarly, if I start with 4, I will go to 4, 3, 5, 4, 3, 5, 4, 3, 5, and so on. It will also move. And these are 3-cycle system, 1, 2, 3, then from 1 to 1 and 6, 5. So it is very difficult to, show the combination of all the states. But this, I think, would give you a basic idea of what the states are. Now, there are certain things where the rules are not allowed. I mean to say, when we talk of a classical system, as I told you, you have seen there is a logic, there is a principle, and there are certain things which cannot be permitted in a, kind of a classical system. So it is not enough for a dynamical law to be deterministic. It must be reversible also. And if you reverse, it will actually come back. So as you remember, Laplace demon said that for such an intellect, nothing would be uncertain, and the future is just like the past. Now, the question what lies is that, can one conceive of laws that are deterministic into the future but not into the past? Can we formulate the irreversible laws? The answer is absolutely a yes. And here you see a reversible system from 1 to 2, 2 to 3, 3 to 2 to 3 to 2. That's it. So it tells wherever you go and where it would be, right? But suppose, as I told you, that suddenly you are at 2, but you cannot tell where you were before that, because there is no arrow which is pointing from 2 to 1. It is only one arrow from 1 to 2, 2 to 3, and 3 to 2. Now, this is something which is called a irreversible system, and this is something which is not permitted. You will see that this kind of a thing which we talk, that suddenly you are at 2, this is a concept which I have explained in quantum field theory, which is called spontaneous emission. Spontaneous means suddenly you are there. And spontaneous emission, like fireflies, neon lights, where the system is emitting a kind of an atom, it will never be able to come back. And that is why it is a quantum system. This is a classical physics system. Because if the energy, when it is come back, okay, now let me give you a very, interesting observation. I'm myself thrilled just at this moment, this thing came to my mind. Now, if I go back to this slide, you see no dissipation of energy. That means no energy is lost during the process of its reversal. This means that the system is in thermal equilibrium. I don't know, Richard, maybe Arudra, if you remember that when we talked about spontaneous emission, did you remember that the photon got emitted and then it was unable to come back to the low energy state because the photon has lost its energy and it is unable to come back. I hope you all remember. I don't have the slide ready, otherwise I would have. Again, I have to upload in StreamYard and so show you. So a photon is emitted, getting infinite number of chances here, 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 here. Where it will go, we really do not know. Even if it is emitted, yeah, Richard Noling remembers, a very good student, I should say, or a teacher. You're a teacher, I remember. Even if it goes back, it is trying to come back, it won't be able to do, because in between this emission and absorption of coming up, it has undergone what is called a loss of energy. So it won't be able to come back. That means it is a dissipation of energy. That means this one to third point, no dissipation of energy happens in case of a quantum system where there is a dissipation of energy. And that is why it is called a quantum system. Now, this is very deep. This is very this is very central. When we talk about quantum mechanics, we say eigenvalues, uncertainty principle, Schrodinger's. No, but we have to basically know the basic root of what makes the difference between quantum and classical system. Anyway, so we saw this ht, and then we get the flip, etc. Now here you see that is an endless cycle. What are the rules that are not allowed? So first of all is that here, when I'm suddenly at point number 2, then I cannot say where is my past, and this is which is called a irreversible system. But remember, this is allowed in case of a quantum mechanics, where spontaneous emission is allowed, and spontaneous emission, if you remember, cannot be described by Schrodinger's equation, and that is why we need Dirac system. So if, and how do we frame that? Simple formula: if every state has a single arrow leading into it and a single arrow leading out of it, then we call it as a deterministic system. That means there should be arrow into it and arrow outside. So we can say there must be one arrow to tell where you are going and one arrow to tell where you came from. So in case of a photon which is being emitted, I get one arrow going out of that photon, but I don't have an arrow which is moving it back. That means it is not a classical system. You see how beautiful it is. Now here, if I reverse this one, that means the arrow which is going from 1 to 2 on the first figure, if I make it 2 to 1 in this way, and from 2 to 3, I make it on the reverse, and from 3 to 2, I make it reverse. So point is that if I reverse the arrows, the corresponding, that means the law is going to fail. That means I from at point number 2, I know where is my past, that is point number 1. And from point 2, I can go to 3, and I can go from point number 3 to 1, 3 back to 2. So this is how actually things happen. And we can also get something which we know. Okay, so till now, so this is something which we call as finite system. That means we get a fixed rules, either it is 6 state, 2 state, etc. But we also have got something which is called an infinite system. So minus infinity plus infinity. And if I mention this n as discrete time steps and n to the points on the track, then the place along the track would be definitely given by n, capital N, n. So now you see, if I get a kind of an equation, again, I'm quantitatively defining that n plus 1 equal to n plus 2. That means if you start at any odd value 2, you will never get at any even value, and vice versa. With an even value, never get to odd. But on the second equation, if you see, wherever you start, you will eventually get to every other point by either going to the past or going to the future. And remember, this is allowed because one arrow is going in and another arrow is going out. We also learned what is called the basic concept of conservation laws. That means when the state space is separated into several cycles, the system actually is contained and remains in that. And this is what it shows. So 1, I'm going to 1, 2, I'm going to 2, from 4 to 3, 3 to 4. So each state of 1 and 2 belongs to its own cycle, and similarly 3 and 4 belongs to the third cycle. So now if I assign the value, for example, C for conservation, then I can assign C equals to plus 1, it is going back to plus 1. C equal to minus 1, it is going back to minus 1. And C is equal to 0 from here to here. So what I'm trying to mean is that whatever the value of C, it remains the same for all time, because the dynamical dot does not allow any jumping from this part to this part. So whenever there is a jumping, there is no conservation. Remember, that means this particular system, if I go back to this is not a conservation because it is jumping. And from here you can deduce the basic philosophical idea also, what is conservation of momentum, what is conservation of energy, and those. So we have to get a state of a system, and we have to see there are no discrete jumps, and C is being conserved. So this is all what I need to tell you. Apart from that, there is only one point which I have not put it in the slide, that these things are not very easy, because given an initial conditions, I think Richard Nording only told that we get chaos, we get the butterfly effect, and a lot of things. So even if we try to measure a particular system, I mean to say initial condition precisely, it is never going to happen. And that is why Paul Dirac's made the famous statement, you pluck a flower on this earth, you move the farthest star. That means everything is very intimately and intricately related to each other. So thank you very much. And those who are watching this live stream, I would also like to tell that what are the areas somebody asked me that I'm covering. I've explained it. I'm going to cover all those things which are there. So you can just wait for a second. I will just tell you quickly what are the topics that I'm going to cover in this entire session. I think that will be something you are all willing to listen. So if you are there, then I would just quickly share with you what are the things that I'm trying to cover. So just be here, and I will just a second. I will just like to. Okay, here is a slide, so I think, yeah, I can just share it quickly and show it to you. Right, this makes things easier. So share screen. Okay, so I would like to show you what I am trying to cover. So those who have not, so for them, I think this is the good part that I'm going to show you. What are the things that I'm going to cover? Okay, let me remove this and make it a little bit bigger for you. So I'm going to cover the nature of classical physics, motion. I'm going to cover integral calculus, dynamics, differential, systems, energy, principle of least action, symmetries and conservation laws, phase space, Poisson brackets, angular momentum, electron and electric and magnetic forces. But please hold on. This is just an overall idea. I'm going to cover a few things more. Let me show you. I'm going to cover first with measurements, motion along a straight line. Then I'm going to cover vectors, motion in 3 dimensions, force and motion divided into 2 parts, kinetic energy and work, potential energy and conservation of energy, center of mass and linear momentum and rotation. Apart from that, I'm also going to cover rolling, torque and angular momentum, equilibrium, elasticity, gravitation. It is going to take a little bit more time. I'm also going to talk about fluids. I'm going to talk about oscillation, waves divided into 2 parts. Why? Because in this wave, I will be covering the waves so that the fundamentals of waves are so good that quantum mechanics, and when we deal with the waves in the quantum physics, it becomes easier. I'm also going to cover a little bit of thermodynamics. Yes, if you want, Karan, I can give you problems. I mean to say, if you really want, then by the end, this is a very good point Karan has told. I think by the end of each lesson, I can give you problems which you can solve and email me. I will check it and give it back to you. I think that makes sense. Very good suggestion, Karan. Thermodynamics, kinetic theory of gases, entropy, and all the laws of thermodynamics. I'm also going to cover Coulomb's law, electric fields, Gauss's law. Okay, here I would also cover a little bit of Maxwell's equation. We learn, we learn to do by doing. Yes, absolutely. What Aristotle told. Circuits, but I'm not going to cover circuits too much because I'm not good in electronics. I will also cover induction and inductance, electromagnetic oscillations, and alternating current. I'm going to say these are actually some things which are basic. After that, I'm going to cover Maxwell's equations, which I've already made a lot of videos, but it is good that I will cover up in the class. I'm also cover up electromagnetic waves, images, diffraction, refraction, etc. This goes under optics. I will cover special theory of relativity, definitely more about matter waves, all about atoms, conductions, nuclear physics, energy from nucleus, quarks, leptons, and the Big Bang. So that is all. I mean to say that is basically the coverage of this entire study. I hope you will like this because this will cover up everything. Somebody today commented that if I can teach BSc physics and MSc, yes, definitely, but all has to start step by step. I think this is a good way to start. So do let me know if you want any changes as far the lectures are concerned or whether it is going okay or not. Because I made a plan that each and every lecture, first, second, third, fourth class, again a revision. First, second, third, fourth class, again a revision. Then again a revision of revision. That means maybe 8 classes together, a big revision. Because let us understand this is not a classroom program. So I hope I think you're not taking notes, etc. So it is all online. And I believe that online things, okay. So Rudra, how do you find it? Is it all going great? Online things will dissipate in your mind, just like energy dissipation. So all you need to do is repeat. And most of the people think that I'm a very conventional teacher, like a chalk and talk. But yes, I'm very conventional. And I believe in conventional things. Already some of the topics covered in bachelor levels. Yeah. Hamiltonian mechanics, I've got a good amount of exercises, Richard. So I will cover up Hamiltonian and Lagrangian also. So yes, I am a kind of a conventional teacher, and I believe that until and unless you constantly repeat, especially over the internet, it is never going to assimilate in your brain. So I'm very sorry if I repeat those things again and again, because this is my way of teaching. Yeah, that is my way of teaching. I am a kind of a chalk and talk kind of a teacher. I don't believe too much in, what you say, what you say, those things like gizmos, etc., to make things. Robert in Ottawa. Okay, looking forward for the lectures. Thank you, Robert. So I don't look onto that. So I keep on. Yes, and when your brains get older, we need to repeat more. Yeah. So I think that repetition and revisions will make things much better. Now, Karan has suggested something. I don't know whether you will agree. Is that not or not? Okay. So Richard is greeting Robert, and Richard is from Australia, and Robert is from Canada. So how is the weather in Canada? I think it is full of snow, and I love those snow. Right. So I will keep on repeating lesson by lesson and so etc. And I think this will become a good video also. So those who want to watch it later can watch. But still, I would say still the videos are much popular rather than the classes. Maybe I don't know, because there are a lot of talks etc. which we are doing in a casual front. Hi, hello, how is your health? How are things getting? Maybe people don't enjoy that, but anyway, I think this is a good way, because I can draw and really like a kind of a board. I can use it over the internet. So that's it for today. I don't know whether I will be back tomorrow, but definitely this week. And I'm planning to make a complete video on classical physics, which we have taught and talked, and we'll make it on Sunday. Yes, I know that I'm boring you with classical physics. Don't worry. I've just got my notes ready for the general theory of relativity, because all my notes are sometimes on paper. If you see my diaries, these are too mathematical. So I don't want to do onto that, but I make a little bit of adventure and story, mathematics with all those things. Look after yourself, folks. Yeah, thank you very much. So I will be also starting with general theory of relativity, I promise you, and with quantum mechanics. Lots of snow in Ottawa. It went south this year. Okay, great. That's low snow. Okay, low on snow in Ottawa. Okay, so the snow has moved to the south. Okay, great. So I will be coming back with a special series of classes on relativity. Oh, one thing I think I have not shared with you. Just give me a second, and I will share this thing with you. And this is extremely important. I don't want any one of you to miss on this occasion. Just hold on for a second. I will just open. Yeah. So I've got this one for you, and I will just take a minute or so. Has plenty of challenges. Yeah, n-body problem, definitely. Okay, so let me share my screen. And this famous Professor Soumitra Sengupta, he is coming on the 28th of January, which is a Sunday. And he is a master in terms of gravitational physics, cosmology, and what do I call black holes, especially in general theory of relativity. He's already working as a Amal Kumar Roy Chaudhary chair professor in the School of Physical Sciences. I don't want any one of you to miss. I talked to Professor Soumitra. I just make a promotional video. He is a very educated, very senior person, extremely humble, and willing to talk to all the students. Especially, he's appeared in India. Maybe Richard and Robert does not know, in India, to many, some of the, I would say, social media talks. Most of the students know him as Professor Sengupta, and he has worked and published a lot of papers on black hole, superstring, supersymmetry, gravitational physics, Hawking radiation, and a lot. So he will be on 28 January. So Richard and Robert, take a note of this, because it would be 8 p.m. Indian time. I don't know what would be the time for Canada and for Ireland. Have a note onto it. If I can be awake, I will be there. Always nice to support you. Thank you, Richard. Thank you very much. So I think this will be a good one. And all the viewers, just a note, you can ask him many questions. He's a very nice, humble person. You will never feel that he is man of such dimension. If you go and search in Google Professor Soumitra Sengupta, you will come to know what amount of research he is doing and what amount of papers he has published. It's a matter of honor for me and Physics for Students to get him on the whole on as a special guest, and let us make the best use of this 1.5 hours so that we can clear up all the confusions and learn from it. Professor Soumitra coming, Sengupta coming on 28th January, 8 p.m. Thank you very much, and thank you for all your support from India and abroad. We'll be back with few more topics on general relativity and classical physics will go on. Thank you very much. Take care and good night.